Now let's look at an example of creating a Bode plot. We'll work through problem 4.9-1a, where we're given this transfer function. H of s is equal to s over s plus 100 over s plus 2 times s plus 20. This only involves a 0 at the origin and first order terms, so no second order term is actually involved in here, but it's a fairly simple one to start with. Again, the first step is to factor out these constant terms, so I can rewrite this. So in every case, for my first order terms, I've got s over something plus 1, and so what I want to factor out in the numerator is 100, and then I'll factor out 2 and 20 in the denominator. And doing that, I can rewrite this as going to be s over 100 plus 1, and then s over 2 plus 1, and finally s over 20 plus 1. Okay. So all I need to note is that in this case I've got zeros at s equal to 0, or and then also in this case at s equal to 100, and I've got poles. 0 would actually be at minus 100, but I've got poles here at minus 2 and minus 20, and then I've got a constant term in front. Let me just call that C of 100 over 2 times 20, or 100 over 40. This constant term, if I evaluate that, 20 log converted to dB of 100 over 40, that's actually equal to 8 dB. And I think I've got enough information now to actually sketch the Bode magnitude plot. What's critical here is I know the location of the zeros and the poles, and then I've evaluated this constant term, keeping in mind I've got a 0 in this particular case at the origin. So let me bring up Semilog Graph paper here. And the horizontal axis is laid out logarithmically. These darker lines correspond to powers of 10. Labeling them appropriately, I want to pick values that kind of encompass the poles and zeros in my graph. Again, I will never get actually to omega equals 0 on the graph, but I cover frequencies between 2 and 100, so maybe a reasonable frequency here is to label this first one as 1, this would be 10, this would be then 100, this would be 1000, and then similarly this frequency would actually be 1/10. So these are my actual omega values, and I also want to pick out a reasonable scale here on my vertical axis, and I've got a bunch of first order poles that are going to go up in 20 dB per decade. So typically these are laid out, these major divisions are in 10 dB or perhaps 5 dB, some multiple or submultiple of 20. So let me see what this looks like. So I'll call this 0, this 10, this 20. So this one would actually be 15 and 5. Of course, this would be minus 5, minus 10, and minus 15 and minus 20 at the bottom. Let me now change colors. I'm going to just sketch the component plots here. I've got my constant term at 8 dB, 5, 6, 7, 8. So that constant term would be just a plot like this. Actually, let me switch to just drawing a straight line instead of freehand. So I can select that point and then go across. My constant term at all frequencies will be at 8 dB. And then I've got I've got a zero term, or 20 log of omega, so that's gonna cross at omega equal to 1, 20 log of omega 0, so that's going to be 0 here, and then increase by 20 dB for every decade. So that would be this straight line, so 0 at omega equal 1, and then 20 dB a decade above, so that's going to be a straight line that continues like that. It would continue in both directions, so a decade below I'm going to be at minus 20 dB. So this is the sketch of the zero term for the 0 at omega equal to 0. For the zero term at 100, recall I'm 0 for all frequencies less than 100. It's going to look like that. And zero term is in the numerator, so I go up 20 dB for every decade there. So here, so this would go on forever. And then I've got the two pole terms to deal with. Again, I got a pole at 2. Now again, the way this is laid out, this is 1, this is 10. These other solid subdivisions here correspond to, well, the first one is 2, 3 is here, 4 is here, 5, 6, 7, 8, 9, and then 10. They get kind of squeezed together here as I get closer to 10. Some of this would be 20, 30, 40, 50, 60, 70, 80, 90. In some cases I've got subdivisions. Between 1 and 2 I've got 5 subdivisions, so this would be 1.2, 1.4, 1.6, 1.8. I've got 5 subdivisions between 2 and 3 and 3 and 4, but only a single subdivision between 4 and 5. Of course that would be 4.5. Out here closer to 10, where things get squeezed together, I have no subdivisions or dash lines between 9 and 10. Anyway, I've got a pole at 2, which is, let me choose a slightly different color for my pole terms here. And I'm actually going to have to, it's changing my, just get that. Now let me select a different color for my pole terms. I've got a pole at 2, that's right here, again for that term. I'm 0 for frequencies less than 2. Then I'm going to decrease at a rate of 20 dB per decade for frequencies above that. So at a decade above 2, I'm going to be down at minus 20, and this line would continue on forever. I've got another pole term at 20, that's going to be right here. So that would be 0, and then again, actually I messed up that previous plot, didn't I? A decade above 2 is actually 20, so at 20 I'm going to be down 20 dB, and then this line would continue ever. So having the capability to make straight lines like this using a straight edge turns out to be very useful here. And I've got another pole at 20, so for frequencies less than 20, I'm 0. So that's this straight line. And then a decade above 20, which is 200, going to be right here, okay, at minus 20. This line would then just continue on to forever. I'm going to just make sure my line goes through minus 20 dB, a decade above 20. Now here comes the tricky part on this. I'm going to graphically add these together. So let me switch pen colors one final time to get the component graph. I'll make that purple. So we start over here to the left, and I'll see I've only got two non-zero components. I've got this line that's increasing at a rate of 20 dB per decade, and then I've got added to that, I've got my constant term. So the easiest place to actually start here is where this linearly increasing term due to the 0 at 0 is equal to 0. So the sum is going to be 8 dB at that point at my constant term. To the left of that, you see this term will be actually subtracting from my constant term, and I know I'm going down at a rate of 20 dB per decade. So 8 minus 20, what is that? Minus 12. So a decade below 1, at 1/10, I'm going to be equal to minus 12. And then this line would actually continue at that same slope. Would continue so that a decade above 1, or at 10, I would be at 28, which is about right there. But I've got this other term that, I'll leave that. I've got this other pole term, though, that actually kicks in at omega equal to 2. And that pole term is going down at a rate of 20 dB per decade. It's going to exactly cancel the rate at which I was going up by 20 dB per decade, and this line would continue on forever. So here at omega equal to 2, right there, I know I'm going to actually level off, okay, until I get out to 20. This next pole term, this should be a perfectly flat line. This next pole term kicks in at 20, at omega equal to 20, and then so I'm going to graphically add it in. So now I'm going to decrease at a rate of 20 dB per decade. It looks like I'm at about 14 here. So I would continue to go down. 14 minus 20 is minus 6, so a decade above 20 at 200. I should be down at about minus 6. That would put me about right there. But then notice I've got this 0 at 100 that kicks in, and I'm going to add it in. It's going up at 20 dB per decade. So when I add it in, I'm going to level off here for frequencies above 100. And then this line, there are no new terms. I've got all my terms added in here. So this graph would then continue like this. So let me see if I can erase some portions of this line that I've extended beyond here. So that would actually be gone. This would be gone. Okay. And then so what I'm left with in purple is a sketch of the magnitude response of this particular system. So I see, for example, at omega equal to 10, I'm getting magnitude response of about 14 dB. For frequencies, above 100, the magnitude response is essentially 0. Remember, 20 log of 1 is 0, so 0 dB doesn't mean that, for example, the output is 0. 0 dB actually means the output has the same magnitude as the input, because the corresponding gain term here is 1. So this would roughly be characterized as a band pass type filter, band pass high pass type filter. It is providing some gain over a range here from frequencies slightly less than 1. We'll see. This is 1/10, 2/10, 3/10, from about 4/10 all the way up to omega equal to 100. I've got a dB response greater than 0, so I'm getting some gain there. For frequencies above omega equal to 100, the output's going to be equal to the input, and for frequencies less than 4/10 here, the output will be less than the input. because in dB the gain is actually negative. So this is a quick and relatively easy way to come up with the Bode magnitude response. Refer to the textbook for a technique for doing the phase response. It's a little more complicated, and I'm not going to cover it in class. Let me do mention one thing though that's helpful can be helpful in doing this magnitude response. You mentioned that a term like omega over omega 0, that's equal to 20 dB when omega is equal to 10 omega 0. A decade above omega 0, this is 10. When omega is equal to 100 omega 0, 20 log of 100 is 40. And that's a 20 dB per decade rate. But this term is actually approximately equal to, very close to 6 dB when omega is 2 times omega 0. So this rate of plus 20 dB per decade is exactly equal to a slope of 6 dB for every doubling of frequency. And a doubling of frequency is called an octave. So for example, if we had a 0 at omega equal to 10, then an octave above 10, which would be 20, we'd be at 6 dB. An octave above 20, it would actually be 40, we'd be at 12 dB, and then we could continue on in that fashion. These are equivalent. Sometimes it's helpful to be able to lay these things out in octaves and draw these straight lines at this slope going an octave above. Other times it's easier to actually go a decade above and then go up or down by plus or minus 20 dB, depending on whether it's actually a zero or pole term. So and the technique's a little tricky. The only way to actually get good at this is to practice. So you'll get some practice in doing this in the homework problems. I will have a handout. Also make the handout available on the website where I'll provide you with some this Semilog Graph paper.